Well, in this video, we proceed to prove this theorem, Theorem 1.1.1, that is the first theorem in the course. Okay, this is a consequence of the definition of mu of a measure. Let mu be a measure on a measurable space, sigma f. Okay, in this case, the measure mu have four consequences. The first consequence is monotonicity, that if A is a subset of B and A and B lies in F, in this case implies that mu of A is less or equal than mu of B. Okay, subadditivity. If A is a subset of the union of AM, where M is equal to 1 to infinity, implies that mu of A is less or equal than the sum of all measures around AM. Okay, continuity from below. If AI converge from below to A, implies that mu of AI converge to below to the mu of A. And continuity from above. If AI converges to above to A, implies that the mu of AI converges to above to the mu of A. Well, we continue to erase to prove this theorem. For the first property, let B minus A equal to B intersection A complement. Okay, this is a liquid relation, and now write B like this. B is equal to A union B minus A. Okay, in this case implies B is equal to A union B intersection with A complement. Okay, this implies that measure of B is equal to mu of A plus mu of B intersection A complement. That's because A and B intersection A complement are disjoint, because A are disjoint with A complement. Okay. This implies that mu de B is greater or equal to mu de A, because mu of every set is greater or equal to 0 for the first consequence of requirement of definition of measure. Okay, this proves the first part. Now we prove the second part. For the two consequences, let A prime M equal to AM intersection A, and let B1 equal to A1 prime, and for M greater than 1, Bn equal to AM prime minus the union of F1 AM prime from n equal to 1 to n minus 1. Okay, construct B and A prime in that form implies that Bn's are disjoint, and the union of bn's is equal to A. Implies that the measure of A, of mu applied to A, is equal to the sum from m equal to 1 to infinity of mu of bm, and this is less or equal to the sum from m equal to 1 to infinity of mu of am. That's because bm is always a subset of am for definition, and this implies from the one consequence of we proved in about 2 minutes ago that is valid for that inequality, and that equality is because that union and the bn's are disjoint. Okay, this proves the second consequence, and we start to prove the third consequence. For the third consequence, let bn equal to an minus a n minus 1 imply bn are disjoint and have the union of bm is equal to A. Okay, for that reason, the measure of A is equal to the sum of m equal to 1 to infinity of the mu of bm. Is equal to the limit when m goes to infinity of the sum from m equal to 1 to m of the mu of bm. And that's equal to the limit from m go to infinity of the mu of an. Implies the mu of an converges to below to mu of A. Okay, this is the fourth consequence. And for the fourth and last consequence, we prove in 2 kicks. Okay, a1 minus an and go off to a1 minus a. Okay, for the third, imply that mu of a1 minus an converge to the mu of a1 minus a. For now, my mu of a1 minus an is equal to the mu of a1 minus mu of an, and mu of a1 minus a is equal to mu of a1 minus mu of a. This is because an is a subset of a1 and a is a subset of a1. Okay, that implies that minus mu fm go to below for minus a, and that implies that mu an go to above to mu of a, and this finish the proof. Okay.